Hi folks, Mrs. Gates here. As we start our unit on energy in physics, I want to take a minute to think through a couple of questions with you together. First of all, what do you already know about energy? I'm sure you've talked about energy in other science classes throughout your science career. Possibly you've talked about things like the conservation of energy, or that energy comes in various forms, or perhaps that work is a way of transferring energy. We will be looking at all of those ideas today. Let's start by looking at this simulation. What things do you notice about this simulation as it plays? I'll put it in slow motion so it's easier to track. What ways do you see energy represented here? There are two main ways that we see energy being represented here. One is the pie chart above the dog's head. What's happening to the sizes of those pies as the dog goes up and down on the track? The key to the pie chart is over here on the left, and green is kinetic energy. Notice that the kinetic energy is almost zero at the top and increases to a maximum at the bottom. Blue is doing the opposite. Blue is gravitational potential energy, and blue gets to a maximum when the dog is at the top of the ramp and comes to zero when the dog reaches the bottom. There's no thermal energy represented here, and the total energy can be represented by the overall size of the pie. One of the advantages of using the pie chart to represent the energy of the dog is that the entire size of the pie never changes. The energy may transfer forms from kinetic to potential, but the overall amount of energy always stays the same. That's what we mean by the conservation of energy. Let's see what happens as we add friction to our system. Notice that with friction, the dog doesn't go as high up either side of the ramp. And there's a new portion on our pie chart, the thermal energy. Friction transforms other forms of energy into thermal energy. That's why rubbing your hands together on a cold day heats them up. And in this case, the dog's energy is gradually transforming from kinetic and potential energy into thermal energy as the friction slows him down. Let's restart the simulation, but this time focus on what's happening to the bar chart over on the left side. I'll slow it down again to see what's happening more clearly. What do you notice about the types of energy and what the bar chart might represent? A couple of things to point out here. The total energy of the system is remaining constant. That bar never changes in amount. But the kinetic and potential energies are fluctuating back and forth, doing opposite things from one another. So that again, the kinetic energy is the most at the bottom and gets less and less the higher the dog goes. The gravitational energy is the lowest at the bottom and gets bigger and bigger the farther the dog goes up the ramp. Let's see what happens when we add friction on the bar chart. The amount of thermal energy is gradually creeping upwards, but the total amount of energy is remaining the same. How is that possible? Well, if you watch how the kinetic and potential energies are fluctuating, they're still alternating back and forth, but neither one is reaching the maximum that it used to reach. There is less and less kinetic energy and less potential energy as it becomes converted to thermal energy through friction. The three main types of energy we saw in the simulation are listed here: kinetic energy, thermal energy, and gravitational potential energy. Take a minute and think about how you can tell an object would have each of these forms of energy. Let's look at kinetic energy first. Kinetic energy depends on an object's mass and on an object's velocity. The faster something is going, or the bigger it is, the more kinetic energy it will have. In physics, we usually use the notation E with a subscript K to represent kinetic energy. You will sometimes see kinetic energy represented with just a capital letter K. Gravitational energy depends on three things: an object's mass, an object's height, and the gravitational field strength. This is abbreviated lowercase g and is our familiar 9.8 meters per second squared on Earth. Since gravitational potential energy is a potential energy, the notation we usually use is the capital letter U. U is used when we are denoting a potential energy. We then add a subscript G to show that this is gravitational potential energy. In our study of physics, we will consider thermal energy and dissipated energy to be equivalents. We will abbreviate them E subscript dis for dissipated energy, or sometimes E subscript thermal, or THM, to mean thermal energy. In most of the cases we consider, thermal energy will arise from the force of friction acting on something. That means that in most of the cases we consider, the amount of dissipated energy will depend on the force of friction and the distance something has been sliding. The last form of energy that we will really study in depth is spring potential energy, sometimes thought of as elastic energy. This energy depends on the amount that a spring is stretched, as well as the stiffness of the spring. Because this is a potential energy, we denote it with a capital letter U and a subscript SP for spring, or a subscript EL, or the full word elastic. Let's practice using the pie charts to describe the energy changes in a system. Consider a situation when a ball is held above the ground and then dropped so it falls straight down. We'll restrict our analysis to the time the ball is moving in the air before it hits the ground. Consider positions A, B, and C and what types of energy the system will have in each of these cases. At position A, the ball is not yet moving, so it does not have kinetic energy, but it does have a height and a mass. Therefore, at position A, our object will have all gravitational potential energy. But by position B, it has lost some of its height, so it will not have 100% gravitational energy at point B. Instead, some of this energy will be converted into kinetic energy as the ball is falling and moving faster. Thus, the total energy in our system is the gravitational energy plus the kinetic energy. By the time the ball gets to position C, right as it's about to hit the ground, its height is essentially zero and it's moving its fastest. All of the energy has been converted into kinetic energy. As we discuss energy, it will be important to think about what objects are in our system. In physics, what we mean by a system is the collection of objects that contain the energy that we are describing. In this case, our system includes the ball that is falling, and because we have gravitational energy, our system also includes the Earth, because the Earth is providing the gravitational field in which the ball is falling. A neater rendering of that drawing is shown here, but the same principles apply. The gravitational energy is gradually becoming less, and the kinetic energy is gradually becoming more. The total amount of energy in our system is remaining constant. Representing the energy changes that happen in a system using pie charts is a powerful tool in understanding and predicting these changes. We will practice these as well as using bar charts throughout our course of study of energy.